In this lab, we're going to test Faraday's law using these two inductors. This big one, which is already hooked up to the function generator, and this small one, which is not yet hooked up. The big one is already connected to a function generator, and we're going to drive that and produce a varying magnetic field. Then the varying magnetic field will produce a curly electric field that will induce an EMF in this coil. So the driving side of the circuit consists of the function generator, a 100 ohm resistor, and the coil, all in series. The resistor is theoretically not necessary, but if we want to get a quantitative measurement of what's going on here, we need to know how much current is going through that coil and creating a magnetic field. We use the resistor that way because by measuring the voltage across it with the scope, we can find out indirectly using Ohm's law how much current there is in this circuit. Now I'm going to hook up channel 1 to the scope so that it's measuring the voltage across the resistor. So I plug the black cable into the grounded side of the scope, and then I have no real choice. That has to go to the grounded output of the function generator if I want to avoid having a ground loop that would short across something. Then for my other connector, I'm going to go from here to the other side of the resistor. And that's why I've arranged the circuit so that the resistor is on the side connected to the black grounded output of the function generator. There's nothing going on yet because I haven't turned on the function generator. Its amplitude is still on 0. Now I'm going to go ahead and turn up the function generator, and I'm turning it up to 5 volts just so I get big signals with a good signal to noise ratio. That can produce very large voltages in this inductive circuit, so as a safety issue you really don't want to go around touching the exposed conductors in this circuit right now. Next I'm going to hook up channel 2 of the scope to my other solenoid. This circuit is not actually directly connected to the circuit that's on channel 1, so that means I don't have to worry about grounds at all, which is nice. So now I've just got this inductor hooked up like that, and this is an inductor with 3200 turns. If I now turn on channel 2 on the scope, I get a small signal on there, and if I move it closer, the signal gets bigger. Also, if I turn it around, I'm expecting the signal to flip, which it does. So now I want to get this receiving coil in a place where I know what's going on with the field of the big solenoid. So I found this Tupperware, stick that in there, and I'm going to put the receiving coil like that. That positions it sort of right at the mouth of the solenoid, which is a nice place to put it because theoretically if you have a half-infinite solenoid at its mouth, the field is 50% of the field on the interior of a large solenoid. So even without doing more sophisticated calculations, right away we get a pretty reasonable guess as to the field of the big solenoid at the location where the small solenoid is experiencing it. We'll go back and measure that more accurately later, but at least it gives us a real quick and dirty way to estimate things without doing anything complicated. So now let's measure both of these signals on the scope. I'm going to turn off channel 2. So now what I'm seeing is the voltage across the resistor, which tells us about the current through the large primary coil. I'm going to move that using the vertical position knob so that the bottom of the sine wave lines up with that dashed line. Then I'm going to measure the peak-to-peak amplitude, which is 1, 2, 3, and I'm going to say 3.75 divisions. And the scale here is 500 millivolts per division. Now let's measure the voltage on the secondary coil, the small one. So I'm going to press the channel 2 menu button, which pops up channel 2. They happen to look exactly the same size, but they're actually on different scales, so that's just a coincidence. And I'm going to turn off channel 1. Again, I'll position it so that the bottom's on that line. And the peak-to-peak amplitude is 1, 2, 3, I think about 3.85 divisions. And that's on a scale of 1 volt per division. Now we need to know all the physical parameters of these two coils. So I measured the length of this coil to be 8.9 centimeters. It says on it that it's 3,400 turns. Those are the only two parameters that would matter if it was an infinitely long solenoid and we were deep inside it. But because we're not, we're going to have to add a correction factor on here, which does depend on the diameter of those coils. So I had to get around in back of it, but the basic idea is by measuring the diameter of the big coil from the middle of the bundle to the middle of the bundle, I got 10.9 centimeters. And I'll summarize all these numbers later, so you don't need to write them down just yet. The secondary coil is a square, and you can't really see the inside dimensions of the bundle of wire itself. So all I did was take a ruler and put it sort of diagonally on here, try to guess visually how far the diagonal was, and it looked like about 3.5 centimeters on the diagonal. And it said on it that it was 3,200 turns. So that should be all the geometrical stuff we need. And I've positioned the secondary coil as close as possible to the end plane of the big solenoid, meaning this plane right here. So essentially I'm going to approximate the secondary coil as being at a point that's in the mouth of the big solenoid in its end plane. And then using the result of a homework problem, we can find the magnetic field of this thing, which is of the big solenoid, which is smaller than the theoretical field of a infinitely long solenoid. So that homework problem is problem 11-13 in Fields and Circuits. So summarizing all those geometrical parameters then, 8.9 centimeters for the length of the primary coil, 3,400 turns, and its diameter, which matters for that correction, is 10.9 centimeters from the center of the bundle to the center of the bundle. And then for the secondary coil, the diagonal across the mouth is 3.5 centimeters, and it's 3,200 turns. Now here's a summary of the electrical measurements. So in the primary coil, that's the peak-to-peak voltage we measured. In the secondary coil, that's the peak-to-peak voltage we measured. Since these are both peak-to-peak, you can just kind of consider their ratio and not really worry about whether they're peak-to-peak or center to peak or something else. The frequency was 1,000 hertz, and the resistor was 100 ohms. And so just to make clear what my notation is, that capital V means the voltage difference across that resistor, from which you can use the resistor and infer the current on this circuit. And then the script E is the EMF measured across the secondary coil. The analysis is a little bit complicated, so here are some hints and guidance. First of all, you might want to try calculating the field of an infinitely long solenoid that had this many turns per unit length, and calculate that at the peak value of the current. So the peak value of the current would be half the peak-to-peak voltage divided by the resistance. So if you work that out using the standard equation for the field of a solenoid, you should get that value right there. Then we have a pretty big correction because it's not an infinitely long solenoid. So the actual field B divided by that B naught is quite a bit less than 1. If you look at this problem in the book, it actually gives you the answer to the problem and you're supposed to prove it. So just plugging into that, you don't even need to be able to solve the problem. You should find a correction factor which is a little less than a half. And the idea is like for a solenoid that's infinite in one direction, you would get exactly half the field of a long solenoid because you could put two solenoids together sort of like that. If they were both half infinite, then their fields would add up to the full internal field of a solenoid. So this comes out a little less than a half because also the solenoid doesn't extend infinitely far to the left. And when I worked out this ratio of the induced signal on the scope to the voltage measured across the resistor, comparing apples to apples here, so peak to peak versus peak to peak, if you want to do it that way, I got pretty decent agreement with theory to within about 20%, which I think is pretty good because a lot of the geometrical parameters were hard to measure accurately, and we're also making approximations about the geometry.